Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. As usual, I'm happy to try to answer any questions, simple or seemingly complicated, about science and technology and mathematics and those kinds of things. And I'll do my best to tell you what I think about different kinds of things. So we have a few questions that I see were left over from last time. There's one from Mikhail here. Are there any models that predict how society behaves? All right, that's kind of an interesting question. It's kind of we have to look at different kinds of scales and different kinds of phenomena. So, for example, let's say you've got a city and you're looking at the growth of the city. Well, it's a good beginning model that the city will grow, the outsides of the city will grow further out, and when there's a road, it will go around the road and so on. And it is possible to make pretty reasonable models that tell you sort of on average how a city will grow. They won't tell you, oh, in this particular place, somebody's going to build a road that's going to cause people to go and continue making subdivisions out in this direction. But they might tell you that the typical form of the growth of a city is things are randomly placed down on the edge of the city. In fact, there's a well-known model that was originally developed for, originally developed actually for tumor growth, and then has been used for many other kinds of things. It's a kind of aggregation model where you have a growing blob, and you say around the edge of the blob, let's add new lumps randomly at different places around the edge of the blob. And that model predicts various things about how you'll get some tendrils that grow out, and you'll get an average kind of roughness of the surface and so on. And that model does sort of okay at sort of on average saying how a city will grow, not telling you in particular, this particular city, what will happen in this particular place. Now, you can so that's sort of one level of kinds of things that happen in modeling society. If you look at an even smaller scale and you ask about, let's say, road traffic flow, there are things you can say about, oh, a traffic jam will tend to develop, and as you go further and further back in the traffic jam, the average time between stops and starts will increase. I think it's like the square root of the distance from the front of the traffic jam, something like that. And those are things that you can work out and that are sort of robustly true, independent of the details of, oh, this particular person was faster at putting their foot on the brake than this other person, and so on. Now, if you ask about kind of larger scale features of society, there are interesting issues there. I mean, for example, the hierarchical organization of certain aspects of government or of large organizations, militaries, things like this. I think there is some evidence that there are sort of general principles of how people tend to organize themselves that are sort of universal to the way things work. I mean, it's kind of like in a company, it's always a little hard to tell when you're doing these societal kinds of things, to what extent is it, everybody says a person should have manage 10 people, and each of those people could manage another 10 people, and so on, that people say that's how it should work, and therefore that's how people set it up? Or is it, oh, people kind of arrange things based on how it seems to feel right and so on, and it ends up being more or less that way? It's hard to tell which of those it is, and which is because people think it's supposed to work that way, and which is because that's sort of the natural way for people to have it work. Now, if you look on a still, if you ask questions about things, I mean, there are all kinds of detailed models that people have about different districts, and if they're people who like, who have this belief in this area and this belief in this area, and how will they tend to where will they tend to live based on the fact that they prefer to live with people who agree with them in this way or that way. There are various models actually based on these things called cellular automata, which I've worked on a whole bunch. There are various models that people have made of those kinds of processes, of neighborhoods separating themselves into, everybody who likes this thing is in this area, everybody who likes that thing is in that area, how that comes to be, and so on. And again, there's some sort of average statistical regularity to how that works, even though the particulars of, oh, does that mean so-and-so is going, such and such a block in New York City is going to turn into this or that, that's not the kind of thing that those models can tell one about. Now, you can also ask more global questions. What kind of theory could you have about the overall flow of history, so to speak? And people have had a variety of kinds of theories like that. Sometimes they kind of say, look, science is going to prove history has to work this or that way, and then they tell people, so you should, so let's make it work that way because science proves it has to work that way. I think generally that's not been a very sensible kind of set of beliefs. But you can ask questions about whether it's inevitable that when some society develops a certain amount of bureaucracy, then this will happen and that will happen. And you can see, certainly anecdotally, one can see as sort of fields of endeavor get larger, they get more institutionalized, there's more structure, things slow down, et cetera, et cetera, et cetera. Whether that can be turned into something that is kind of a model. Maybe we should talk a little bit about what the point of models is. So there have been, I think, maybe three, maybe we're just introducing a fourth kind of general epoch in the history of modeling of things. So back in ancient Greek times, what did it mean to make a model of how the world works? Most of all, it meant, what's the world made of? Is it made of a bunch of atoms? Is it made of everything is water or something underneath? Or what are things made of? It's kind of the structure of what's there. And then the big innovation of the 1600s of people like Galileo and Newton and so on was, actually there's another thing one can do, which is to use mathematics, mathematical equations, to work out what should happen in the world. We have an equation that tells us the pattern, the geometrical figure that the Earth will make in going around the sun, things like that. It will go in an ellipse, et cetera, et cetera, et cetera. And that one of the features of that kind of mathematical epoch of modeling was, we can say we take things that we see in the world and we turn them into a mathematical formula. And then one of the things that we can do with that mathematical formula is that formula will be true for all time. And so we can say, well, if we want to know what will happen in the system, if we want to predict what will happen in the system, we just have to use that formula and plug the appropriate number for the time in and then get the result. So that kind of mathematical approach to science led people to the idea that, oh, a big part of the story of science is about predicting things, is about being able to say, from what we know now, what will happen in the future. And those kinds of predictions mostly are precise predictions. That is, specifically, it will rain tomorrow, or specifically, this particular planet will be in this particular position tomorrow, and so on. So that was kind of the idea of a lot of modeling for a very long time. And clearly in things like, will it rain tomorrow? That was a very challenging area to be able to use kind of mathematically inspired modeling to predict, but gradually over the course of the last 60 years or so, people have gotten better at running models of the atmosphere and being able to work out, what will the weather be like. But again, it's not so much roughly it's going to rain 20% of the time on this time of the year, and it's going to do this percentage of the time. You actually want to know specifically, is it going to rain tomorrow? And even though there may be some slight uncertainty in that, the fundamental objective of modeling is to know with specificity, is it going to rain or not? Okay, so then the kind of third epoch of kind of making models in science was one that I think really started in earnest in the 1980s, and I guess I take some credit for having initiated this. It was kind of the idea of, don't use mathematical formulas to describe how the world works. Instead, say things follow these particular rules that can be represented as computer programs. If you run that program, it will behave in a way that corresponds to the way that the world actually behaves. And so that allows you to say, if you've got this, this set of rules that describe how a snowflake grows, you run that set of rules as a program, and then you make these pictures and you say, is that the correct description? Is that a correct representation of how snowflakes grow or not? So that's something which you might think it's just like the mathematical paradigm. It's going to make precise predictions in the same way. And sometimes it can. But there's a very important phenomenon that I found in the 1980s, a thing called computational irreducibility. And so here's the story. You say, okay, you say, I've managed to figure out the rules by which this system operates, the precise way in which the components of the system work and how they're related to each other, what they do through time. I've got a program that I can just run that will reproduce what the system does. Okay, great. Then that means, you might think, I can predict everything about what the system will do. Well, there's a catch. The problem is that process of running the program, you might have to go through all the steps that the program goes through to work out what will the system do some amount of time in the future. From the mathematical paradigm, you kind of have the idea, I just plug a number into a formula and I immediately jump ahead and say what will happen sometime in the future. But what happens in this computational paradigm is this idea of computational irreducibility, that it can be the case that to figure out what is going to happen in the system, you basically have to follow each computational step. It's an irreducible amount of computation that's involved in figuring out what will happen. And that's kind of a very core phenomenon of this kind of computational paradigm. And so it means that you can have a situation where you can say, well, yes, I have a pretty good model for, let's say, some aspect of how society works, and it's governed by these rules. But if you say, well, what's going to happen? It may be a case where you'd have to say, well, I've got to run the computation to see what will happen. And really, that's, in a sense, no more efficient than to just observe what actually happens in real life, so to speak. So this idea that, okay, once we've got this model, then we can immediately kind of jump ahead and say what will happen is not the case anymore. And and sometimes one can make overall statements about, well, this kind of a thing might happen. And or there are these characteristics of what happens. Okay, so one of the things that's very recent, last couple of months actually, it's an outgrowth of this big project that we've had to understand the fundamental theory of physics, is a kind of a new paradigm for modeling that I kind of call the multi-computational paradigm. And let me not get too deeply into it here, but basically the main point is that it's a way of thinking about things in which there isn't just a single thread of time. There's not just a rule that says, from this moment in time, we work out what will happen at the next moment in time, and so on. There are multiple threads of history, and the rules describe what happens on each thread of history. And each of these threads of history, they can branch, there can be multiple different things that can happen at a particular moment, or they can merge. It can turn out that different sort of threads of history lead to the same outcome, and so on. The thing that's really interesting about this multi-computational paradigm is it seems to be a pretty good model. It seems to give you pretty good raw material for modeling lots of kinds of things. And it has the feature, well, it has a necessary feature is, if you say, well, what happened in the system? There are all these different threads of time. You can't immediately say, well, this is what happened. Instead, you have to say how an observer is sampling what's going on in the system. And it then turns out that with sort of observers that are at all like us as kind of human observers, there can be certain very general features of the behavior that you see in a multi-computational system. And that has big consequences for understanding how physics works. But I also suspect it has consequences in other places, possibly in places for understanding kind of the evolution of society and things like that. But I don't yet know exactly how that will work out. But one of the things that that tends to suggest is that there might be robust sort of laws. People had imagined back around 1800 or so that just as people were figuring out physics, so they thought at that time, that there would soon be a social physics, which was as much a predictive theory of society as the physics of the time was a predictive theory of the motion of planets and things like that. It didn't work out that way. The question now is, can one have something which can make sort of statements, global statements about laws that govern sort of things in human society, for example. And it might be that that's the case, but it will not be. The question is, what are those laws about? They're not going to be about the specifics of, so then this particular event will happen. They're not going to be about that. What they might be about might be things where we might say, well, that's a weird feature of society, which we never thought to think about before. And yes, there might be a law about that thing. And then given that there is a law about that thing, a way of saying what will happen, a way of describing what will happen, and so on, then perhaps we can use that to build, just as we built lots of engineering around the things that we can predict will happen, particularly coming from the mathematical paradigm. So we might imagine doing similar kinds of things in society. But it's I think that the general problem is a complicated one because, well, a particularly notable feature of models about how humans behave is are those models affected by the fact that humans can know about the models about humans, how humans behave? One of the things I've always found surprising is if you look at things like the behavior of people on the web, clicking on things. They click here, they click there, they have certain time distributions between when they click on this and when they click on that. A lot of those results, if you look at it in the aggregate for a large number of people, are incredibly precise. They're incredibly precise curves. Nobody can really say why they come out the way they come out, but they're very robust and repeatable about kind of the behavior of people on the web. So there's some aspect of our behavior that is, in some at least statistical sense, quite predictable. But if you kind of if you ask, yes, I mean there are things like that. There are kind of small scale things like that that are predictable. If you say if you look at different areas that involve, oh yeah, I was going to say in the financial area, it's a sort of classic example of where people say, oh look, I've noticed this regularity in the stock market or something. And they feel very pleased they've noticed this regularity. And they say, well, given that regularity, I can make money by knowing that I can make some small prediction about the stock market. And therefore, I can use that by some clever piece of financial engineering to be able to make money from the stock market. And what tends to happen is that once somebody has discovered that and other people notice they've discovered it, then things change in the market and it prevents that ever working again. Now, having said that, there are plenty of people, including people I know who have been in the quantitative finance world, who have had particular schemes for kind of beating the market, and they have kept working for a very long time, partly because sometimes the sort of technological foundation that you need to execute those schemes is large enough that even if somebody else said, oh, I know how that scheme works, they wouldn't actually be able to do it. But that's a place where sort of knowing the humans knowing what the theories are about how the humans behave can have an effect on how the humans behave, although it doesn't seem to have an effect at the level of, how quickly do we click on things and so on, but it may have an effect at the level of more global scale. Now, of course, in a sense, if it is to have an effect, one of the main ways it will have an effect is through the fact that people know enough about history to know, gosh, if this is happening in the world, then if we don't do this, this is inevitably going to happen because, gosh, it's happened 10 times before in history that way. And so it's sort of an interesting and strange thing when people say, oh, history is irrelevant. We don't care about history. The world is now in a special place. It's never been like this before for one reason or another. Let's forget about history. That's in a sense denying even the thinnest thread of possible kind of understanding of the progression of how things work in the world. And I would tend to think that in a sense, the denial of history, you might think that you would say, we don't need history to understand the future of the world. We can just do that with science. But actually the first step in doing that science might be to just say, well, what's the history of what's happened? I mean, that's the first kind of stage of of doing scientific things is to say, well, you know, what's happened before? It's and that gives us some expectation about what will happen in the future. A long answer to that. Oh, you guys are asking complicated questions. Okay, there's a question here from Cutoff. What knowledge helps weather prediction and how? Weather prediction is a question of maybe I think I've talked about this actually once before. Maybe I should refer to the previous time I've talked about this. I think I did spend some time talking about weather prediction. So let me skip that for the time being. Let's see. My gosh, there's a question from Aaron to me about when I count in my head, do I count verbally or visually or in some other way? You know, I don't know. I always used to think when I was a kid that I was totally dysnumerate, that I just couldn't do things with actual numbers, because I definitely would have a habit, and still do have a habit, of like counting on my fingers. I suppose one of the things that one learns, and perhaps having spent a lot of time dealing with computers and writing computational language and so on, is how to not make mistakes when one does things. You know, computers are a great sort of place to learn how to not make mistakes, because if you write a piece of code and it's slightly wrong, it's going to do the wrong thing. And you know, if you wrote a piece of English, for example, and it's sort of slightly wrong, well, people still might understand it, it might kind of be okay. But when you write a piece of computational language code and it says the thing that's different from what you wanted it to say, it will do the wrong thing. And so it's been something that I've certainly noticed about myself is how do I do things slowly and carefully enough that I just don't make any mistakes? Because typically the experience is once you've made a mistake, fixing the mistake is always vastly harder than not making the mistake in the first place. And you know, once you made the mistake, it's like, oh, then you go and you do a whole bunch of other things. You spend hours doing things on the basis of this thing that turned out to be wrong. So, you know, when I'm writing code and things like that, I tend to like to, you know, every little tiny fragment of this, you know, symbolic program that I'm writing, I'll just run it, see what it does. Does it do the right thing? Okay, I go on, I assemble another piece. Okay, assemble another piece, and gradually I sort of slowly build it up. And I think sometimes, you know, people might watch me do this and it might seem sort of painfully slow and deliberate, but that's partly because over time I have learned that there's certain kinds of things, don't do that too fast because you'll get it wrong, or at least I'll get it wrong. And so it's like, okay, I really want to know how many of this thing there are. Okay, let me count very carefully and deliberately, and I'll sort of group things in groups of 5 or something, and then I'll add the things up in my head and so on. And it's kind of a laborious process, but I think I tend to be a count on my fingers type person, or at least verbally say things, not something very, very visual, although I do tend to like to sort of group things so that I can know, oh, that's a group of 5, and I know it's really a group of 5, and that's another group of 5, and I can add them together and so on. I mean, this challenge of not making mistakes is, I mean, one has to not be absolutely obsessive about it, because then one ends up not sort of being able to do things at all, but it's still something where I think an important issue is to know when to have a good sense of whether you are pretty sure you're right, or whether, oh, there's a possibility I made a mistake here. And, you know, I think that comes a lot when it's a question of understanding things. And I think over time, I've gotten progressively better at understanding when I understand things, and understanding when I'm, it's still a little bit loose, I don't really quite understand it. So if you ask me something about it, I can't necessarily tell you the right answer. So let's see. RJ is commenting, if you write enough errors in code that cancel each other out perfectly, your code is perfect. It's very hard to have errors that cancel out in that sense, because once your code is doing something, it will do something in one place. It will, maybe it will, I suppose you can have a situation where, oh, you thought you were generating a list of numbers, let's say, but actually sometimes it can be a list with no elements in it. And okay, that's a thing. And one might think, oh, that could make something go wrong, but maybe later on, and oh, you're going to make a picture based on these things, but if the list of numbers has no elements in it, the picture is going to look goofy. But then it turns out that later on, you filter the pictures based on this or that thing. And so even if there was one goofy one, that would be dropped out when you filter them. And so that error is kind of washed away. I think that is my impression is that that's a very rare case where things are kind of robust enough, where things kind of get to the point where they're kind of smoothed over by something later on. I tend to think, having spent a lot of my life doing design of computational language design, the real job of the language designer is to make a language where people typically write correct code. And if the language is confusing, people will often write wrong code. If the language doesn't give you enough kind of framework about how to think about things, people will end up doing very complicated things where things can go wrong. For example, if you're writing low-level, if you're writing in a standard low-level programming language, you're often writing, a loop that says for this variable equals this, do this, add something to the variable, add this to the thing you're working on, et cetera, et cetera, et cetera. It's really one step at a time. And if you make any mistake in any of those steps, the whole thing's toast. In kind of our Wolfram language, one of the things we try to do is to take the kind of cognitive lumps that you think about things in terms of, and make those be the things that you're using in the computational language. Have those be the things that have names. So like you might have a name like table, make a table of values of a thing. And rather than, oh, let's take this variable and add something to it and append things to make this list, et cetera, et cetera, et cetera. It's like there's this one thought that is a clear thought that we can have. Oh, I want to make a table of these things. And you can have that thought. You can immediately get the computer to do it. You're not fiddling down in the details where there's a lot more possibility of error. You're rather taking kind of your thoughts. Now, of course, the computer can force you in when you try and represent something in computational language. If you don't know what you're talking about, then the computer's going to catch you out. Because when you write something in computational language, it is a definite thing that you're saying. And if you're kind of vague, if you kind of wave your hands, as I'm waving my hands right now, and sort of say, it roughly works like this, that's kind of not good enough. It's actually very much the same with mathematics and mathematical notation. If you write sort of precise mathematical notation, you kind of have to commit yourself to, oh, it's defined this way. It's not like, oh, it's vaguely this or that. Now, I have to say that there are plenty of times in thinking about things where saying it's vaguely this or that is a place where sort of human intuitive thinking is very important and allows you to just leap over huge amounts of detail that can in some cases get filled in later. One of the things in terms of thinking about things is, one thing is you go one step at a time. You're always, you always know what you're doing. Everything's very precisely defined, but you're walking one small step at a time. And to get a big distance is a lot of steps. The other alternative is you have an intuitive grasp of how things will work, and you jump 1,000 miles in front, and you figure out this is roughly how it has to work. That can be extremely important to do that, because once you've done that, it's much easier to go through those detailed steps and go in that direction, because you at least know what direction you're going in. Otherwise, you're taking these detailed steps and, oh, you might make a wrong turn, and then you're taking these detailed steps off in another direction, and you don't know what's happening. So for me, it's very important to have this kind of intuitive ideas about how things should work out. And then it's great to be able to particularly have a computer fill in the details. And so when I think about things, I might think in sort of general terms about something, and then I say, well, how will I turn that into a computational language representation? And that process of turning things into a computational language representation is one where kind of a lot of issues that I was sort of vague about get nailed down. Let's see. There's a question or comment here from Jonah. How do we improve our inductions towards producing creative results in science? Are scientific inductions probabilistic? How lucky can I get with an induction towards the proof of a thing? So what is scientific induction? It's kind of an idea that, okay, so why is there science at all? Fundamentally, it's because there's order in the universe. There are definite regularities and laws that govern how the universe works. It's not self-evident that the universe should be that way. It's not obvious that the universe should be at all comprehensible to us, that it should be possible for us to describe the universe in terms of comparatively simple laws for how things work. It's not obvious that every time we drop something, it falls under gravity in the same way. It could be that every time we drop something, some detailed difference happens. If you look at, I don't know, you're looking at the ocean and you're asking, when I put something on the surface of the ocean, how will it move? Well, every time you put it down there, it's probably going to move slightly differently because there's a slightly different piece of swell, or there's a little wave that's different or something like that. It could be that everything about how the world works would be such that there wouldn't be a global law that describes it. It would always be special case, specific example, etc. The fact that there is regularity in the universe is a very fundamental thing. It's a very fundamental kind of philosophical, theological, whatever point about the universe, that there is regularity in it. Now, I have to say that in recent times, I have come to believe that the reason there's regularity in the universe, at least as we perceive it, is because of the way that we perceive it. That underneath, ultimately, the universe is not a very regular place. The universe is a place where sort of, in some sense, all possible things happen. But the way that we sample the universe and the way that we we choose to knit together our perceptions of what's going on kind of is what leads us to these kind of comparatively simple laws for the universe. And so in a sense, the nature of our consciousness is what leads us to believe that the universe follows simple laws. And we could, if we were some alien consciousness or something, we could end up with a completely different set of laws that the universe should follow. And I think, in fact, there are really two sort of axiomatic features of us that lead us to conclude that the universe follows simple laws. One is that we are computationally bounded. That is, if we want to know every detail about what's happening in the universe, where every gas molecule in the room is going, all those kinds of things, we don't do that. We don't, our brains, our minds are just not capable of following all those details and doing all those computations. We are computationally bounded. We have to summarize things in simpler ways. So that's one sort of feature. The second feature that turns out to be pretty important is the idea that we believe that there is a single thread of time in the universe. That is, that sort of we can remember the past, we can go into the future. There is a single thread of history that we're following, that we're not saying, oh, there are these different things that happen and then they merge together and so on. Now, in some sense, in reality, in the universe, I'm pretty sure that there are all these many threads of time and so on. It's just that our sampling of the universe doesn't notice that. And in fact, whenever there are things which are following these multiple threads, we are conflating these things together. And that's just our way of sampling what happens in the universe. And that's a sort of crucial feature of how things work in the universe. I mean, something somewhat related to this idea of sequentialization in time is things like the possibility of motion. The possibility that even though the microscopic structure of the universe is different here and here, it's still the case that I can move my hand from here to here. And I think of it as the same hand that wound up in the second place in the first place, even though at a microscopic level, if one looked down at the sort of level of the atoms of space in our models of physics and so on, they will be different atoms of space when my hand is here and when my hand is here. Nevertheless, for our purposes, at the level of understanding of the universe that we have, we consider those the same. And those are things that are sort of our way of parsing the universe. So our way of understanding how things work in the universe. And I think that's what leads us to conclude that the universe follows fairly simple laws, has a certain kind of regularity. It's a kind of self-fulfilling, self-inflicted conclusion. But anyway, the end result is, so the universe follows comparatively simple laws. There are, you set up more or less the same circumstances, more or less the same things will happen, all those kinds of good things. So that is really the basis for science. If it wasn't that way, it would be, you would just have to say, well, the universe chooses to do this today and chooses to do something different tomorrow, and we can't really make a general formal scientific statement about what the universe does. Okay, but when we want to make a formal scientific statement about what the universe does, how do we conclude what that statement is? How do we decide what the universe is really doing? Well, the only tool we have generally thought that we have to determine what the universe is really doing underneath is experiments. We say, let's try doing this now. Let's try dropping this ball now. Let's try dropping this other thing now. Let's see what happens. Okay, we do it 10 times. Well, then we say it always does the same thing. Let's characterize how it works. Okay, it follows this particular law of motion. So then we can say, okay, we've seen it do it 10 times. Gosh, that must be the way it works. And that's the notion of scientific induction. If we've done the experiment a certain number of times, then we can conclude that really is how the universe works. And we can then extrapolate from that to say, okay, whenever we do this experiment, it'll always work the same way. There's nothing unexpected and miraculous that could happen. It's just a sort of a repeatable scientific idea. So it's when you ask the question, given a small amount of data, 10 observations, what can you conclude from those 10 observations? Can you conclude it always works this way? Well, of course you can't conclude it always works that way. You only got 10 observations. The only way you could conclude something more global than from those 10 observations is if you have a sort of Uber theory, a theory that tells you about the set of possible theories you might have. Because, for example, if you say, my theory has to be described by a mathematical formula that is of this type, and it roughly looks like this, then you can make much more definite conclusions from just making 10 observations. Let's say you've got a coin, you're flipping it, and you say, my coin is described by having a certain probability, a certain independent probability of coming up heads or tails. And then you flip the coin 10 times, and 9 times it comes up heads. Well, then it's a sort of exercise in statistics, mathematical statistics, to work out what is the probability, given that the coin has 50-50 heads or tails, intrinsic probability. What's the probability that it has 75-25 intrinsic probability, and so on. Given the observation, you invert it, typically using Bayes' theorem, to say, given what I observed, what does that imply about what the underlying actual probabilities were? Now, the catch is that unless you have some a priori, unless you have some initial sort of Uber theory, you can never answer that question. You have to have that initial kind of Uber theory about how the world could possibly be, and the distribution of possibilities, what the likelihood is that the world, for example, is governed by a law that involves 5 parameters versus 10 parameters versus whatever else. You need that kind of Uber theory in order to make a conclusion from a limited observation. Once you have that kind of Uber theory, then yes, you can say there's this probability that this is the correct specific theory, this probability, this is the correct specific theory, and so on. Now, what's happened in the course of people doing science and methodologies in science and so on is people are always coming out with And now we have a model-less prediction, a non-parametric, it's often called, not involving, let's say, a specific, not involving some existing formula where you're just tweaking parameters. It's a non-parametric, it will just find the theory based on the data without any uber theory, without any prior assumption about how the theory works. Every such claim is a fake. And that people regularly, every few years, there'll be another reason why somebody says, and now we can do it this way. So the most recent one of those is with neural networks. People say, oh, we can just use a neural net with machine learning and so on to say, let's look at this data and let's work out a model that will be encoded in the neural network for this data. And it's a non-parametric, it's a model-less model, so to speak, but it's not. It is, if you look at what a neural net of a certain size and so on, what kind of characterization of the world can it give? There's a certain characterization it can give. If I used a different shaped neural net, so to speak, with more layers of computation or whatever else, I would be able to represent a different set of things in the world. It's, even though people say, I've got such a general model underneath, it's really a model-less model that I've got here. It's never true. It is necessarily the case that there is always an underlying model, an uber model, whatever, however you want to position it, so to speak. There's always a more global thing of which your particular model is supposed to be some instance. And so one can start asking, well, what's the best uber model that we can have? Now, this is where it gets a little bit interesting, because in the past, those uber models tended to be very mathematical models. They will be things like a very common type with so-called general linear models, which are just straight line dependence of this and that, and mathematical formulas basically. Or you might have some other simple mathematical formula. It might be a Gaussian distribution, a particular e to the minus x squared distribution that is a pretty common thing to occur, and then you tweak the parameters of that. So those are the sort of typical models for things. And why should those models work? Well, for example, in the case of Gaussian distribution, here there's the following fact. So basic fact in mathematical statistics is called the central limit theorem, and it says the following: if you are randomly picking values, let's say they're values between 0 and 1. Okay, so you get 0.2, 0.7, 0.3, 0.4. You just pick a bunch of those values and you pick them at random according with some probability for each value, for each of those possible values to occur in between 0 and 1. Okay, if you take more than, I don't know, 5, maybe 10 of those values, and you just look at the average of those values, you say, I'm going to take buckets of 5 values, 10 values. I'm going to just look at the average of that bucket of values. That average is distributed according to this Gaussian distribution with quite high accuracy. In other words, whenever you take averages, it ends up being the case that you get this kind of bell-shaped distribution where the most likely value of the average is kind of in the middle, and where there's a progressively lower chance of getting values further off in the tails, and you get this kind of bell curve distribution where it's known that if there are different many details of that curve are very commonly talked about, things like confidence intervals, 2 sigma, standard deviations, all kinds of other sorts of characteristics of that curve are widely talked about. The reason that curve is so widely talked about is because if you just take a bunch of numbers and you're always taking averages, that'll be what you typically get. Now, there are footnotes to this central limit theorem. The footnotes are about, well, exactly how are those numbers initially picked? And how are those numbers distributed? Could there be a really huge number that isn't between 0 and 1, but it's as big as 100? Could there be an unboundedly large number? Things like that. There are a bunch of footnote conditions to the central limit theorem, which in practice, in the real world, often sink it. Or, for example, another one would be, oh, the numbers can be anything, but if they go below 0, you're toast. If you go below 0, let's say you're looking at the price of a stock. If it's below zero and the company is worth a negative amount of money, that doesn't happen that way. The company is bankrupt at that point. And so so that changes the way this distribution works. So in any case, this idea of what is the correct sort of ultimate model for the world is an important one. And people have sometimes thought this is particularly prevalent in medical research, that everything is a Gaussian distribution. It just has to be. It's not true, simply not true. I mean, for example, if you look at the distribution of human heights, it is generally, well, I have to say, I haven't looked at this data for a while, but it used to be the case, at least, that human heights were pretty accurately Gaussian distributed. Nobody really knows why. It's presumably the effect of many genes that have an effect on height, and you're sort of taking their linear average like that, but nobody really quite knows why that is. If you look even at human weights, they are not Gaussian distributed. They're not distributed according to the Bell distribution. They're distributed according to the skewed distribution that has a bigger tail. And if you look at, I don't know, medical test results of different kinds, you'll find all sorts of distributions that are sometimes normal distribution, sometimes Gaussian distribution, but often not. And quite a lot of the statistics in medical research is based on the assumption of Gaussian distributions. And people often quote these p-values and things like that. That's all based on, maybe I'll explain it some other time, it's all based on features of this Gaussian distribution, this normal distribution. Which just aren't always correct. Okay, but so then the question is there a best model for how things work in the world? And if one's going to just sort of fit things to some model, what's the best way to do that? Well, there are two ways I can imagine sort of anchoring that. One is to know how physics really works underneath, and the other is to know how we work in terms of our way of perceiving things. So in terms of how physics works underneath, I think one of the great achievements of our physics project in the last couple of years has been getting a pretty good understanding of what the machine code of the universe looks like. And from that, it's a long way from what's happening at the a trillionth of a meter size in space-time to what happens in everyday life. But it gives us some foundation for thinking about sort of what is the ultimate model for things in the world. And the one thing it tells us very clearly is that computational models are ultimately the way the whole universe is put together. Now, whether it could be that there's a computational model that works at that trillionth scale, but that isn't the right model at a large scale. But it seems like it is pretty good evidence that this computational model idea is a good idea from the fact that it really works at that machine code type level. Okay, so that's one kind of model. So the other kind of thing is about our perception of the world. How do we perceive the world? What do we even notice in the world? Well, what we notice in the world is largely determined by how our brains are set up. So for example, when we look around at a visual scene, we tend to break that visual scene into objects. We say, there's a camera there, there's a computer there, there's a, whatever it is there. And rather than, we have this notion of sort of clumping things into objects. Well, that's a feature of the way our visual system and our brains work. And so when we start saying, well, how does, what should we make science about? We will start saying, well, there's this object and another thing that does this and does that. We notice the things that our brains are able to perceive. There may be other details about how the world is working that we just don't notice because our brains are not wired to perceive those things. So when it comes to making models, if our models are sort of plugged into the way that our brains perceive things, then that's a good leg up in terms of having a model that reproduces those aspects of the world that we're likely to care about. So in other words, and that kind of is probably why when we look at things like neural networks for machine learning, why they're not so terrible at making models of some kinds of things, like, for example, I don't know, the folding of proteins or whatever else. They're not so terrible. And the reason they're not so terrible is less to do with the underlying physics and more to do with what we care about what's happening in the physics, because those are the things that we have been choosing to look at. We're not choosing to look at the detailed dynamics of the microscopic motions of the proteins and this, that, or the other. Rather, we're just interested in what overall shape is the thing going to make. And that's something that is more, something that more operates at the level that our brains operate at. And that's, I think, a slight argument for why there is a little bit of a leg up to models that are based on the same kinds of things that our perception is based on. So that's kind of a so if you're asking how do you get to do scientific induction better, I think there are those two anchor points. One is kind of what the fundamental machine code of the universe looks like, and the other is what we know about how we perceive things and what is worth including in a model to be able to say the universe works this way, at least as far as we will perceive it. There may be many details to how the universe works that are wonderful and very rich and complicated, but we don't happen to perceive them. So it's not so important to capture them in a model that we make. And by the way, I thank you for asking that question, because quite a lot of what I had to say there was a clarification to my. Let's see, there's a couple of questions about flipping coins here from Techno. Which side of a quarter has better aerodynamics? And from Riff Tracks, if a quarter was flipped by a human 100,000 times on a windy day and another 100,000 times on a non-windy day, would the overall outcome still be 50-50? Well, look, here's the point. If you have a machine that flips coins and the air is still, you can make a very repeatable experiment. You can flip it with a certain velocity when it's flipped from the artificial finger, so to speak, and it'll go flipping around in the air. If the air is still and the air is in the same state every time, the coin will turn over a certain number of times and then go and land on heads or tails, and it will be completely predictable. There's nothing that makes that unpredictable. Now, the reason that coin flipping seems kind of random is because even the slightest difference in the speed that the coin is made to go up at will cause the number of times the coin turns around in the air to be off by 1. And off by 1 is enough to go from heads to tails. So that it's because there is, let's say it turns over 20 times in the air. Then in a rough approximation, if you change the speed with which you flip up the coin by 5%, because your finger is not accurately producing the same force to within 5%, you won't be able to determine whether the coin will land up heads or tails. So in a sense, what's happening in coin flipping is you're kind of being sensitive to the initial conditions, being sensitive to the precise speed that you flip the coin at, and you're also being sensitive to the environmental conditions, like was there a puff of wind that moved the coin slightly this way or that way. So the fact that you say, oh, coin flipping is random is really because the thing that's doing the flipping, you haven't completely determined how that works, because we just don't have that level of precision. But if it was a machine that was carefully machined and so on, and all carefully set up, then you could make it completely predictable. And I think this question about which side of a quarter has better aerodynamics, and I don't know how accurately when you flip coins, let's say you ask the question as you change it's a slightly tricky question. Remember, actually, I did write some stuff about this in my New Kind of Science book, in one of the 1,000 notes at the back of the book. One of them is about coin flipping, and I did talk about this question about what it even means. Let's say you say, as you change the speed that you flip the coin at, and you can make a plot. There's even a picture in the book there of what happens. The sort of black and white stripes according to whether the coin is going to land up heads or tails based on the speed at which you flip the coin. Now, it's a pretty tricky thing what you mean by, oh, I'm going to flip it randomly, because you've got, well, it's just, it's not random between speed 0 and the speed of light. That's definitely not what you mean. You mean there's a certain sort of typical range of speeds, and exactly what that distribution is like is going to determine the exact probabilities of different things happening. Because it isn't the case that the coin flips 100,000 times in the air. It flips maybe 20 times. I don't know how many. I think when I was working on this back 25 years ago or more, I actually did try and unfortunately, we didn't have cell phone cameras and things like that. It made it a lot easier back in those days to actually do the kind of freeze frame photography to see just how many times does it flip over. But let's see. It's a question from WST. How do you end up with a different set of rules while describing a system with definite observable behavior? No matter how alien a consciousness is, the rules will remain the same. Well, yes, the rules for what underneath happens might remain the same. The question is, what do you care about in what happens? So a really classic example that I keep on referring back to, and it actually, strangely enough, it was the version of this question was what really got me first seriously interested in fundamental physics 50 years ago now, back when I was like 12 years old or something. Here's the thing. We see, we have gas molecules bouncing around in the room. We say, what do we care about the dynamics of a gas? Maybe we just care about the overall pressure. Maybe we care about the velocity, the speed of the gas. We move our hand through the gas and it's moving out in certain directions and so on. What do we care about? There is many, many, many details about how these gas molecules are bouncing around and so on. But most of the things that happen, we don't care about. So when we talk about sort of an alien consciousness representing something in a different way, what we may be talking about is the fact that there is a different set of things that have been perceived. And so there are different laws that govern those kinds of things, because we have certain laws that govern pressure and temperature. But if we make up, I don't know, ooogleriffousness made up by some alien, ooogleriffousness will be some characteristic of the details of molecular motions that we would say we don't care about that, we don't measure that, we don't see why that's important, but to the aliens that's the most important thing about the gas, and it will have different laws. And so that's how you end up with these very different descriptions of what is at some level quotes the same thing. Let's see. A question about how to spell the word that I just made up. Sorry, I just made that word up. It didn't come with a spelling. I mean, it's an interesting, the story of how you spell words is always an interesting one. In different languages, some languages are phonetically spelled, as in the way the word sounds, you can immediately deduce how the word will be spelled. Some of the languages like Russian, which had a definite written language constructed sort of in recorded history, were set up that way from the beginning. English, we weren't so lucky from a spelling point of view. There were a bunch of bright ideas back in the Middle Ages where people said, when we write a word, let's encode something of the meaning of the word right in the word in its spelling, even though we don't say that. And for somebody like me who's done computational language design for a long time, these kinds of, oh, that was a bright idea about how to encode meaning and so on, I always pay attention to these things and I wonder if it was right or not. I mean, a classic example, I don't know, the word debt in English spelled D-E-B-T. Where's the B? We don't say the B. Well, back in the day, it had been spelled D-E-T-T, but people decided to add the B because it was like the Latin word debitor, which has the B in it and which means the right thing. And it's like, let's encode the meaning in the spelling of the word, even though we're not going to say those letters when we say the word. And that's, were it not for that decision, probably spelling bees would be a lot less interesting in English, because one would have potentially a purely phonetic way in which words are spelled. And even the standardization of spelling is a comparatively recent phenomenon. I mean, I think last 150 years, I think you see the sort of full standardization of spelling, and you go back further than that, definitely not a standardization. Even among people's names, that somebody will spell it one way one time and another way another time, and maybe that's because they only said their name and some other scribe or something wrote it down, and one time they transcribed it one way and one time they transcribed it another way. So I think, but this question about it's an interesting question. Well, actually, the general question of what makes a reasonable word is an interesting one. I've certainly thought about this question in connection with things like naming products, naming areas of science, things like this. And the frustrating thing I always find is that when you make up words for things, sometimes the words are really obvious and you immediately come up with them. Like, for example, a word that I recently started using is ruleology, the study of systems with simple rules. And that's kind of an obvious name, ruleology, for studying things with rules. But I've been thinking about what that thing should be called for 30 years. And I've come up with a lot of different possibilities that are based on Latin and Greek and so on. And unfortunately, in the area of things like rules and structure and sort of autonomous behavior and so on, most of those words have been used for things we know well, like logos is used for logic, logistics, all these kinds of things, and all the ology type fields, or something like rules. I think in Greek archos, or that's more a ruler in Greek. But that leads us to archaeology and archetype and all these other arch words that, archaeology would have been a great name for the study of rules based on Greek meaning of words, were it not already taken for the study of ancient artifacts and so on. I don't actually know quite how the ancient artifacts version of archaeology got that meaning. I would have liked to have that meaning, but I was 500 years too late for that. But so it's a curious question. What makes a word sound reasonable and not sound reasonable, be memorable, not be memorable, and so on? We certainly know that there's a certain amount of regularity in the structure of words. I mean, from there are certain combinations of letters that occur more often. There's certain combinations of sounds that occur more often. There are some fashions in what kinds of sounds might be good ones to occur. I mean, the use of X in English, there are endless product names that are from the last 50 years or so that are X-based product names. Although one of the early ones, Xerox, strangely, that particular one, its X was not added for sporting value, so to speak, in the sense that it wasn't put there as a matter of just like let's X it up in a kind of because X is a cool letter. Xerox came from the name xerography, which was the process of dry. It was kind of a Greek named version of a photocopier of that type was based on xerography, and that comes from the Greek word xer, which means dry, and graphy, which means writing. So it was kind of a dry writing thing. I mean, okay, for the sake of having a technology moment here, it's like, how does a laser printer work? How does a photocopier work? It uses the fact that gosh, it's a long time since I thought about this. It uses the fact that you can have a plate, used to be made of selenium. I'm not sure if they're still made of selenium. And it has the following property, that you can have it be the case that where light falls on this plate, there will be, you are causing it to electrically conduct, and where it doesn't fall, it doesn't electrically conduct. And so what? So then the idea is that you have the image from your piece of paper or the thing you're trying to print or whatever else, and that is that. If it's from a piece of paper, it will be actual light. If it's a laser printer, it's a laser using its light to scan across the plate, and or it's usually a drum. In actuality, the thing is usually a cylindrical drum, but conceptually it's a plate. And then in some places where the light falls, electricity is conducted, and the charge, you charge up this plate, and in places where the light falls, it's discharged, so it doesn't have so it doesn't have this electrical charge. Okay, so you have this plate which has this complicated pattern of where it's charged and where it's not. And then what you do is you get these plastic granules, and you sort of sprinkle those plastic granules on the plate, and they stick in places where it's charged, and they don't stick in places where it isn't charged. and that's the so-called toner that's used in laser printers and photocopiers and so on. And that's what, and so what then is happening is in places where it sticks, it's got black or whatever else it is, then you put a piece of paper next to that and you bake it on with heat. And that's how you produce the image on the piece of paper. So that's kind of the process of both photocopying and laser printing. Laser printing, again, instead of having the light from the original image of the piece of paper, you're sort of synthesizing that image by having a laser that's scanning across the plate or the drum, and it's kind of going one line at a time to specify what the content should be there. The reason that it was sort of Xerox and so on was proud of the dry copying. Was that the previous generation, in my youth, there used to be a variety of copying technologies that involved liquids, and where you would do things like you would expose a piece of paper that had some kind of, it was more like a photographic process, where you will be essentially developing it through this liquid. And it was all a very messy process with liquids and so on. So that was sort of the big innovation, was of dry copying. All right, maybe one or two more, and then we should wrap up for today. Okay, RBS says, why can't logic be easier to understand? What I mean is all this academic stuff that teaches logic, it seems Greek to the person who's saying this. When I try to learn, I get bored fast because they explain it in a too complicated way. Well, it's worth understanding logic has various aspects. I mean, the original idea of logic, probably due to Aristotle in 4th century BC, roughly, was what Aristotle was doing was, when people make arguments about things, somebody stands up and says, the people of Athens must go to war with Sparta because of this and that and the other, and et cetera, et cetera, et cetera. They make an argument. They say, if this is true and that is true, if it's not true that this and that are true, then blah, 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 then not this or not that must be the case. And you make these arguments, and the arguments have a certain logical structure. What Aristotle wanted to do was to classify those logical structures, to classify the structure of arguments. He'd been, at other times in his life, he was classifying, mollusks, types of mollusks and things like this. He was very big on classifying things. And in his more philosophical work, he was into classifying causes of things. And, the material cause, the formal cause, oh my gosh, what's the other one? There's 4 of them. The final one is the final cause, but I'm missing one of his causes. There's a second cause, and I can't remember what that is. In any case, just classifying kinds of things. But one of the things he classified was forms of argumentation. So that became a type of logic called syllogistic logic that for more than 1,000 years was taught to people who were supposed to be being educated. And people taught a little bit of mathematics, they taught rhetoric, and along with that, they taught logic. And it was kind of neck and neck with mathematics as a thing that was taught. And people would memorize these forms of argument. They actually had mnemonics, like I think one was called Barbara, another was called Celerant. And those letters stood for particular structures of argument. And you could kind of memorize, oh, if I make a this and that and whatever. So then in the 1830s, it became a lot more mathematical. George Boole particularly kind of figured out how you can really think about it in terms of and or and not, and really just think about things more like mathematical variables. P means, is it raining or not? P can be either true or false. Q means, do I have an umbrella or not? And then you kind of can make things that go together, P and Q, things like that. A person who did a lot of work in kind of sort of popularizing logic symbolic logic, this idea of, P's and Q's standing for statements about the world, was Charles Dodson, better known as Lewis Carroll, author of Alice in Wonderland and so on. But he also wrote rather nice books about logic, trying to sort of give everyday versions of this kind of way of describing things in terms of logic. Now, the fact is that way of describing things in terms of logic, with our mathematics and our computers, we can crush it. If you give any kind of combination of not P and Q or R and not P and this and that and the other, you give this very, very complicated thing, we can be very precise and say this is the truth table of whether the result will be true if all these different inputs are true or false. So we can take that whole expression and we can simplify it, and we can say, is there any set of truth values for the inputs that will make the whole thing true, et cetera, et cetera, et cetera. It's a decidable mathematical theory. It's something where there is a systematic procedure for answering the question, how will this work? How does that work in logic? So that style of logic, so-called propositional logic, a logic of propositions like it is raining today, that kind of logic is something that with our modern mathematics and computers and so on, we've completely nailed it. We understand everything about how it works. And from a human point of view, it's how useful is it in actuality of tracking arguments as Aristotle wanted it to be? It's mildly useful. People make the most horrendous mistakes in not thinking kind of logically like that. But I would say that the more elaborate forms of logic are more relevant because they are the way that switching circuits out of which computers and other things are made, they work according to logic where they're a little, a gate, a transistor implements a single logical operation, usually a NOR operation. One might have a billion of those things all put together that actually does what our CPU chips do and so on. But that was sort of the form of logic. Propositional logic was kind of the earliest form of logic. There's another form of logic called predicate logic. It's a little bit more elaborate, invented. Well, it began to be invented in the 1600s, but got serious in the work of people like Gottlob Frege in the end of the 1800s. It's the idea of saying, rather than P as a proposition, P and Q, blah, 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 of having these so-called quantifiers, things that say for all. So let's say all, the most famous one, all men are mortal, Socrates is a man, therefore Socrates is mortal. That's actually in the form of a syllogism, but the for all, it's true for all something that this works. There are two quantifiers that one usually uses, for all and there exists. So you might say, for all sheep, it's true that they're white. And then you might ask, does there exist a black sheep? And then you could sort of prove that from one thing that the other thing is not true. There are no black sheep, et cetera, et cetera, et cetera. Logic, by the way, has the feature that whatever you put into it is what you get out of it. So if it turns out that actually, I think it was when Australia was when people went to Australia and noticed that there were, people said all swans are white until they went to Australia when there turned out to be a black swan there. I think that's the story. And sheep have different colors and so on, but you might have only seen white sheep. And it's like that scientific induction question. Can you, from the fact you've seen 100 white sheep, can you conclude that every sheep is white? I mean, it's like there's this story told. It's kind of a story told with various kinds of scientists in the story. And I think a common version of the story is like there are 3 science types on a train, somehow in Scotland. I don't know why in Scotland was part of this, but and they see a sheep out of the window, and there's an economist. And the economist is a very generalizing scientist who says, oh, so it must be the case that all sheep in Scotland are white because we've seen this one white sheep. And the physicist says, well, all we can say is that there's this one sheep that's white. And the much more precise mathematician then says, no, actually, all we can say is that one side of one sheep is white. But of course, this is a question of how far can you take the scientific induction? And in different fields, there are different expectations for different kinds of modeling and so on that get done about how far you can do that. But let's see, I was talking about logic, and just to sort of finish that thought, the logic, as I say, what you get out is just what you put in. So for example, a very common feature in logic is the logical implication function in propositional logic. It's, if P, then Q, okay? And one of the things that's absolutely crazy in some ways is that in standard logic, implication, if P, then Q, has the feature that if P is false, then for any Q, one says that the implication is true. So from something that isn't true, you can infer anything. That's a very weird and screwy claim that doesn't really accord with a lot of things that we think of every day, but that's the way that the structure of logic, of propositional logic, say things should work. So anyway, so the logic is usually propositional logic, then predicate logic, and then you get into different special forms of logic like modal logic and temporal logic, where you have things about, things like about time. For all time, it is true that whatever. For all times after this, it is true that whatever. Or logics where you say, there is a possibility that whatever, or sometimes a probabilistic logics, it's probable that whatever. You can make these various logical calculi, and there's a question of sort of how do they agree with or not agree with our everyday sense of how the world works. In a sense, they're scientific models. They're like scientific models of they're like kind of scientific models of the everyday world. And they're not particularly good scientific models of the everyday world. They're very good models if you're building a computer that has transistors that act like precise logical gates. But if you say, what does this mean for sort of our overall understanding of the world? It's not that good a model. And people have sort of tried to build kind of physics reasoning kinds of ways to do things based on sort of just making logical inferences about the world, and they really pale in comparison to what you can do with sort of the more mathematical computational approach to studying those kinds of things. But in any case, in terms of logic, the other sort of mathematical logic then kind of emerged from things like predicate logic. Also emerged partly as a way of representing mathematics using logic. And that gets very abstruse and complicated. And there are many foundational questions that bite us in the design of computational languages and things that are also foundational questions in mathematical logic, having to do with, particularly issues of reference. If you have in mathematical logic and in computational language, there are things like variables, but there are all kinds of issues about, you say, I'm going to put a hat on the duck. Okay, and that's your function, put a hat on the duck. Okay, the problem is that, the question of which duck, well, you have this thing, this function says, put a hat on the duck. And then the question is, well, how do you refer to which duck you're talking about? And how do you know it's that particular duck, the one that's called Jim? And, or it's that particular, and then it's, well, is that enough to specify the duck and so on? And you get into these questions, which are sort of a mixture of things about the real world and things about kind of the structure of a formal language that get quite complicated. And in fact are quite unresolvable without some kind of appeal to either what you're trying to achieve or how the world actually works outside. And yes, there are very abstruse things that happen. If you, last December was the 100th anniversary of the invention of these things called combinators, which were a great step forward in many ways in mathematical logic, which have really not been well understood. They're certainly not widely understood. For 100 years, they've not been widely understood. I mean, I myself have made use of some aspects of how they work in the design of our computational language. But if I tried to explain that to people, and that was how it works, it's like an incomprehensible thing. I would say that one feature of combinators, the one thing that just makes them super hard to understand is they are a way of describing things without using any nouns. They never name things. They always just say, that thing over there combined with this thing over here, combined with that thing that's first there, et cetera, et cetera, et cetera. They're always just specifying plumbing of how you get sort of information flowing from here to there, but they never actually name a thing. They never say, I'm going to call it X. They just say, it's the thing that goes from here, goes to there, et cetera, et cetera, et cetera. We humans have a very hard time with this. And it's, you know, when you look at combinatorial expressions that represent, in a sense, this plumbing of take this data from here to there and then do this with it, it's really incomprehensible to us humans. And I've certainly been curious whether there's a way to kind of make scaffolding in human language that gets to the point where that's comprehensible. I haven't succeeded in doing that. Okay, I should really go here. All right, well, there's some interesting questions. Maybe we can start with them next time. All right, well, thanks for lots of interesting questions, and I look forward to doing this again next week.